Okay, Agriya, you are also a moderator.
And yeah, also just like public, we do like on GitHub reviews of like who wants to talk, how do we go about doing it, blah 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 blah. At least my speaking.
There's a lot of noise, Rahul. I don't.
Yes.
Yeah.
I see folks are still joining in, so I'll probably wait for another 2 minutes to uh, give a brief intro about SciPy to the audience present here, and then we can get started with the talks, if that works. Oh,
It would also be great if some of you guys, some of us can come on video so that we can see each other's faces. You can blur your background to hide the mess in your room, as I have done.
I was just trying to save up some data. Hi, everyone.
all right. I think this should be a good time to just give a brief intro about SciPy, and I hope I'm audible and visible, by the way. So cool. Right. So thank you, folks, for joining, and I think people are still coming by, but I'll yeah, just we'll get started with a brief intro, and also I'll try to keep it brief so that we have some more time to accommodate the talks, which tend to go sometimes, here and there. So SciPy is essentially this is a community initiative that we did recently. Its first inception happened here in India back in 2009, when there was a very niche, small community of folks who were interested in scientific Python, scientific computing, and they used to do small meetups in person. And I believe there was a yearly conference every year till 21, which I think was conducted in one of the IIT campuses. Was uh, one of the go-tos. Correct me if I'm wrong, Agriya, by the way. But um, and 21, if you look at the actual website also right now of scipy.in, you could see the archives and all the previous meetups that happened. We just felt, and especially I'm one of the core volunteers along with Malaysia, Agriya. I'm not sure if Aditi is present on call. We met at the India FOSS conference, which happened recently in Bangalore. There was a FOSS and Science dev room that was conducted, and we just felt that this audience, the audience that came to the dev room, was uh, an ideal audience to target for a to start the SciPy conference again. And so far, we have had this is our third community call, so we have had two community calls before this, and yes, it's essentially a community-driven initiative. Almost all the, I mean, for the speakers might be aware of this, but all the proposals, Everything literally is open source. We have a repo set up, which includes the source code for the landing page, and yes, so we're just excited. We hope to conduct an in-person conference next year, based on the feedback and the traction of these community calls that we get. And yeah, that's just a brief about the SciPy, and I'll probably hand it to Navya so that we can get started with our first talk.
Yeah. So good afternoon, everyone. I'm Navyasai Sadhu, a third-year undergraduate in computer science and engineering, and a former summer fellow at FOSS. I'll begin sharing my presentation now. So today I'll be talking about OpenFOAM and a node editor for generating its case files. What's OpenFOAM? It's an open source software for computational fluid dynamics. It solves the math equations that describe how fluids move and behave. It could be the air flowing over an aircraft or water through a pipe. It is used in academia and industries like aerospace, biomedical, and so on. Let's get to the core workflow. One begins by defining the geometry, the shape of what you're studying. Say you're studying vascular flow, then you'll probably need a 3D geometry of aorta model. Divide that into multiple cells leading to what is known as a mesh, and then set the initial and boundary conditions such as pressure and velocity. You would have to choose a solver, pre-built programs in OpenFOAM that solve specific types of fluid flow problems. For example, Icofoam solves incompressible flow to calculate velocity, pressure, or temperature of each cell dynamically, which are later seen and studied using ParaView, a software to visualize process results. Think about it, with all the physics and math behind the steps along, might be intimidating to the beginners already. The case files and its syntax can act as a steep learning curve for them. Not only that, the manual editing might be error prone. Thus, a node editor acting as a visual programming interface for generating the case files was built. Before getting to know how it was developed, I would like to tell you about the file structure and the basic IO format of OpenFOAM cases, which will be helpful further. Each case has a zero folder containing the initial velocity pressure conditions. Constant folder has the mesh data and physical properties. And the system folder has solver settings. Coming to the IO file format, it consists of the dictionaries lists, which are the common data structures used. Every file starts with foam file dictionary that contains metadata like version, class, format, etc. Scalars are just numbers, vectors are 3D coordinates, and tensors are 3 by 3 grids. If you know basic high school physics, yeah, you would have known that. And dimensional units are just set of 7 physical units to prevent mistakes during calculations. So a node editor had been built earlier, but the one I built is more modular as it uses the PyVNT library developed at FOSS. What it does is it creates node trees that mimic the OpenFOAM dictionary hierarchy. It provides with container classes named NodeC for the dictionary and KeyC for the key value pairs in it. It also provides with property classes for various properties like integers, floats, lists, so on. It provides with a parser to read the existing form files and to convert them to node trees. It also serializes node trees back to the file format. One can also set a custom element order, we'll see later in the demo. As much as it makes our work easier, it restricts the development of node editor to some amount. Some of the provisions like macro expansion, file imports, which I did not detail upon, are not available yet. The application uses MVC architecture to separate different concerns. The PyVNT library handles all the data, validation, and open form specific logic as the model. The GUI built using PyKitty 6, a Python framework for building desktop app, provides the canvas for nodes, menus, and panes. The application logic connecting the view and model acts as the controller. It handles the user events like clicking, dragging, and certain methods. When I began building the basic app with the scene, menus, and panes, I did not think over the data types and understand the file structure that well, and ended up creating nodes for each dictionary instead of creating for each of the PyVinty's node classes. Also, I could not come up with an eager evaluation, something that's used in editors like Blender, and turns out there wasn't even a need for it. After brainstorming, I realized a need for method which would return the PyVNT object only during the file generation by the PyVNT serializer, boiling it down to a lazy evaluation. And that was my eureka moment. Eventually, the node's self-contained visual blocks representing the OpenFOAM files data types were programmed, followed by the sockets, which are connection points on the nodes with inputs on the left and outputs on the right, which also have a compatibility check so that only the right nodes connect to the right ones. The edges connect the sockets, showing the data flow from one node to another. Two specialized nodes for generating case files were created. One creates a single file while the other generates the entire case directory. Some of the features used in normal node editors like knife tool to cut the edges, undo redo stack, tabs, and user guide were implemented. The other way around was also taken care of. One can create nodes from pre-existing case files, import them, and edit them to make new ones. One can also save the intermediate node system they have created to work upon later using YAML files. So before going ahead, I would like to show a quick demo of the application. So I would like to also show what this is what the case folder looks like, and this is what initial condition texture file looks like. You get the idea, the foam file dictionary I talked about here. And these are the key value pairs. I'll also run the application here. We have the nodes and input, output nodes. These are all consist of the view and are built upon base graphical node. All the other nodes, the container nodes and property nodes I talked about, inherit from it. And I have PyVNT library installed here. I'll run the main and so this is the desktop app. We have the scene, the canvas here onto which the users can drag their nodes. We can pan and zoom in. So this is a key value pair, which I will encapsulate into a key node, which is then encapsulated in a node C, which provides a dictionary. And every foam file has a node C as the root. So essentially acts as the case file itself acts as a dictionary. So I will connect this to this, and to an output node and validate it if it follows the syntax properly, and then put it in a folder if you want, or yeah, and then generate. Oh, I'm sorry. We can see the output created in the output folder here. So this is the dictionary into which we put our key value pairs. One can also import a pre-existing file.
Rahul, are you the moderator of this call? Hey, Philip. Sorry about that.
No problem.
Let's just hope we will be able to get back more super early.
Hi, everyone. We were facing some issues with the previous link, so we've created a new meeting link. We'll wait. We'll wait for a couple minutes for people to join back. A couple more minutes, Vivek. So as other people join, sorry about that issue. We had some issues with the previous link, so we've set up another link now. So maybe one more minute for people to join.
Oh yeah. Yes.
Srihari, should we continue with Navya's?
I believe, yes, she was towards the end of her presentation anyway, right? I think we can accommodate that, and
Yes.
the breaks can be
Short.
swiped off, yes, shortened, and then we can. And yeah, it is on time anyway, just a few minutes here and there, and I think that should be fine.
Makes sense.
Yes.
Can you guys please
Also,
tell me where did I left off? Like when did I disconnect?
sure. This
Do you want
was.
to share your screen?
Yeah.
It was during the live demo. I think for me, it was when you were connecting the nodes and you had shown the output directory on
Okay.
the ID. Yeah,
I'll just continue with the presentation then.
yeah, that works. Again, sorry about the
Yeah,
technical
it's
hiccup. Yeah.
So these are some lessons that I wanted to share during my tenure, which I learned, is that one should commit often and commit messages that clearly describe what changed, which I did not do and ended up regretting later. And always try things out first, experiment a lot, and reach out if you're stuck for too long. Document everything properly. uh, one can contribute by fixing the bugs one can find, or there's one feature that I could not implement is that one can try to enable users share the output of one node to multiple other nodes to reduce the redundancy. Of course, there are many other contributions that can be made once the Pi20 upgrades. There are a lot of features to be implemented. And these are the resources that I used, and you can check out. Do ask out if you have any questions. That's all. Thank you.
Thanks a lot, Navya. I think if I didn't see any questions posted on chat, and I hope there weren't any in the previous link or the previous call. But like Navya mentioned, you can feel free to reach out to her, and especially considering the technical hiccup, I think we can start with Philip's talk soon. So yes, handing it over to you, Philip.
Okay, let's just see if everything works as planned. Just a second. Right. Can you see this? Yeah, I think it should be fine. Yeah?
Yep, all good.
Okay, fantastic. So shall I start? Right. So this talk should be about 20 to 25 minutes. So I'm going to try and sort of talk you through a package this is very, very basic package called Astrolab, which is something that we developed at Ashoka University. So I'm currently a postdoc at the Niels Bohr Institute in Copenhagen, but you'll notice that my affiliation from there is not on this slide. That's because all of this work was completely done at and for Ashoka University. So, and the idea is, and the reason that I'm going to talk that this package was developed was because there was an astronomy minor at Ashoka, and we needed to do a bunch of courses for that. And one of the courses that we were developing was a laboratory course, and it's been quite a successful course, and people enjoy it quite a bit. But I'm going to describe a little bit about the motivation for creating such a package, and then move on to sort of using it for some stuff. So yeah. Here we go. So what's observational astronomy in the way? Like I'm going to make some sweeping generalizations. I should also point out that I'm not really an astronomer. I work on complex physics. So it's just that this is a hobby that I sort of have done on the side. So I'm going to make sweeping generalizations. You're perfectly allowed to disagree with me. But the four basic axes, in some sense, in my opinion, of observational astronomy are imaging, which is the stuff that most people talk about when it comes to astrophotography, nice pretty pictures of nebulae and galaxies and different objects, and you can extract some information from them. But you could go further. When you just take this image, you can actually count the number of photons that are coming from the different stars, and you could do something with that. So for example, you could count the number of photons coming from a star, and if you suddenly see a dip in this number and then a rise again, you could guess that maybe, for example, a planet has come in between you and the star. And therefore, you could estimate that there is that there's an exoplanet transiting this star at the time, for example. So that in that sense, you're actually counting photons. But you still do this with an image. You could also do something else, which is that you could take the data from this light, you could take out all of the light, and you could split it out and get a spectrum out of it. This little rainbow of light from the star, and you could see the characteristic features in this spectrum, and that's quite an interesting thing in itself. And this is an entire field called spectroscopy. And the fourth is a little bit more, like a little different from this, and it's called timing. So this one good example of timing is something very recent, which is gravitational wave detection. So you have these two sort of massive objects that are sort of spiraling in, and you get a time series signal out of that. And this could be one way of measuring like a timing event. But there's something that's not so like fancy as this, but also very interesting, and that's ideas of something like a double line spectroscopic binary. And what you have here is two stars that are orbiting each other. And because they're orbiting each other, they each give out light and a spectrum like the one that's down here. And because they're orbiting and because of the Doppler shift, the spectrum actually tends to oscillate. And so you actually see changes in the spectrum. So up here is some real data from on 2 different days, on the 12th and 13th of August 2000. And you have the same star spectrum. And if you look at the right-hand side, you see the 2 little spikes, and that they've actually moved closer on different days. And that's because of this sort of movement of the stars between themselves. So you can't see these stars actually move because they're too small. I mean, the angular separation is too small. But you can actually measure it this way. So I'm talking about all of these different things, but I won't talk about all of them in the talk. But this is mainly to explain, sort of situate my code in this sort of bigger framework of observational astronomy for amateurs, and to try and reproduce these 4 axes in some way in the lab. So what I'm going to do now is I'm going to replace observational astronomy with my little Astrolab code, and I'm going to talk about how it can do things like imaging. And you can see over here, these are images that we took from our rooftop in Sonipat in Haryana. And these are very similar to the images that we talked about earlier. And you have the same type of nebulae, of course, not as pretty as Hubble's data, but still quite interesting. We can also do photometry from these images. You can actually count the number of photons that are coming out of it. You can actually, by putting something called a diffraction grating in front of the camera, you can actually take a spectrum out of this, and you can also understand the different elements that are present inside the star. And all of this is data that we have collected on night skies in Sonipat. And the last is, of course, the idea of timing. And what we do here is we simulate an acoustic version of a spectroscopic binary, which is just 2 speakers that are rotating. And because the Doppler shift at first order approximation is very much like for sound the same as for light, you can put them together and you can get this sort of very similar sort of system where you have these 2 lines that go apart and then come together. This is an interesting set of analysis. So I'm not going to talk about all these experiments. I'm going to restrict myself to 2 sets of experiments, imaging and photometry, because they are roughly the same spirit. I was also not 100% sure what type of audience this was. So I don't know whether people are experts at science or not so expert at science. So what I decided to do was make this an extremely pedagogic talk. So it's possible that many of you already know much of what I'm going to say in terms of coding, but maybe not everyone has developed, say, a pedagogic tool for people. So maybe there will be something interesting there. So the idea, of course, is, what is the motivation for this package? Well, we have this course, and it's a first-year course. So it's a lab first-year course, and the labs in Ashoka in general are very hands-on. So people like to go collect their own data, do all of their work themselves. And this particular course has tended to be quite interdisciplinary. So about half the class is usually a first year, and the other half the class is also physics undergrads, but there are also people from other courses as well, like history, political science, and so on. So these are generally students who have no real knowledge of coding. So that's one problem. So you can't ask them to, start coding from day one. So you, of course, give them a bit of a primer, but there's a difference between being able to write code and sort of intelligently writing code, and sort of writing code in a sort of framework that can be used to build larger and larger projects. So what can we do? Well, first idea that I sort of had when we did this was this notion. I mean, I do all of this in retrospect. Okay, so but I asked myself what I was thinking at the time. But the basic idea is progressive complexity. Like, it should work. Like, it should work in its most basic way, and it should do pretty much what anyone would think it should do. But it shouldn't frustrate people. It shouldn't be so simple that it can only do one thing. So you should allow beginners to be happy with it because it does what you expect it to do. But it also allows novices or quote unquote experts to be able to do whatever they want with the code. So that's an interesting sort of thing. And you'll see that I've tried to implement that in the little functions that we have in this package. The second is, I don't know whether this is very important for other people, but for undergrads, I find this very important, which is that you need to see what you're doing. You need to look at what's happening, and you need to visually understand whether this is making sense or not making sense. So all functions have little print log attributes. You can decide whether you want to print a log or not, and you can actually understand what the algorithm is doing. So you can, test it out first and then remove all the logs and run the entire code. Then the most important thing for me was to actually reproduce realistic workflows that exist in astronomical data processing. So we try in this code to sort of mirror the same processes that real astronomers use. And the idea is to eventually develop an appreciation for the workflow in more complicated software like IRAF and different software that exists already for this. And remember that, all of the stuff that's being done here has been done much better in other software. So the point is not to get, this fantastic software that does things that nobody else does, but rather to have something very simple that undergraduates can sort of relate to. And the last is, of course, in this vein, to build an intuition for what you're doing. And so, you may run certain commands in more fancy software, but what exactly goes on behind them? What are the underlying assumptions? That's what I hope the code will be able to do. So how does it actually do this? Well, this is the data that we collect. So I should just flash this up on the screen. So we have two little telescopes. We have a bunch of cameras. We have undergraduates. You can see samples of all of them in this image. And I'm going to say that, okay, at the end of the day, we have data, and the data is just an image. And what we're going to do with this is what I'm going to talk about in the later slides. So the first one is, of course, the first experiment I'm going to talk about is imaging. So up here, you have the pretty Hubble images, and I'm going to do a nice little transition and overlay them with the images that we have taken. I like this so much, I'm going to show it to you again. Hubble image, our image. Quite cool, right? To be able to do this in Sonipat on a very, very polluted sky. And of course, it's nothing compared to the Hubble image, but it's not that far. If you squint a little bit, they look the same, which is quite cool, right? So how did we actually go ahead and process this sort of data? Well, I'm not going to go into this in great detail, but I'm going to talk a little bit about sort of the physics of image reduction, where you have camera sensors, which basically are photodetectors. They collect photons and they produce some number of electrons that are proportional to the number of photons that they collect. But the amount of data that you get from astronomical sort of sources is extremely faint, and you would ideally want to stretch this data out, which means that small fluctuations, little bits of noise also get amplified out. Oh, I'm so sorry. It's my sorry. Is this better, Malija, or yeah? It's okay. Okay, sorry. Anyway, so
Sorry, I think it is rubbing against the zipper of your sweater.
I see. Okay, I hope it's not, but let's see. If this is okay, let me know. So right, so we have, with these sensors with noisy data, we have a possibility of a large amount. There are many possibilities of noise. And so what we really want to know is how to remove this noise. And these are not things that affect normal photographs, because the amount of signal in these normal photographs is much higher. But for astronomical data, it's very low signal. And I'm not going to go into this in great detail. This is an entire experiment in our lab. But the basic idea is that you take a light, which is the raw data that you process, and you take some calibration frames. And then you perform some actions with these calibration frames to account for this data. And so what you have on the top here in this sort of three-dimensional model is a 3D model of my image, where the height is the brightness of that particular pixel. And you can see that there's this gray platform on which the image is sitting, and that's called the dark and bias current. And then on top of it, there's this sort of not so constant, weird, wavy sort of platform that this is sitting on top of, which is the flat field. And these are all pixel related issues. And this is the actual image that you'd get. And it looks like this object is very bright. But it turns out that if you actually implement the reduction of the image, in other words, if you actually correct for all of these sensor issues, then you'll end up with something that looks very different. And the way that we correct for it is that we subtract out the contribution from the calibration frames that we call the darks and the biases, and we divide out the contribution from the flats. And when you do this, you have a very different landscape. And you'll notice that what was earlier the smallest peak actually turns out to be the largest peak, and that the locations of the peak have shifted. And there's a lot of interesting stuff that happens. But basically, if you want to do real science, then if you really want to do real science, then you really want to be able to measure the actual number of photons, and that's going to be very important. So this is just to sort of describe the basic ideas of image reduction. So how do we actually do this in Astrolab? So the idea is that you have an image, sorry, not in Astrolab, but how do we actually do this? Well, you have an image. So this is an image of the Ring Nebula that I showed you earlier. It's very stretched, so you can't see the details of the nebula. But what you can see is that the image is not really very flat. Like there's a region here that's very, very bright. And one might think that this is actually bright because there's something in the sky, but in reality, no. It's because of the calibration frames. And I'm going to show you the 3 types of calibration frames, and you can immediately see that this contribution from the dark is what is responsible for this. So then there are some processes. You stack these guys together, you produce masters, you then subtract the unreduced image from the dark divided by the flat, and we end up with this nice, pretty reduced image. And you can see the clear difference between the two of them. This is a much flatter image. It's taken into account all of these things. So how do we actually do this in Astrolab? Well, this is the code that does it. In the first line, you import the package. In the second line, you load the image as a 2D array like this, a bunch of numbers. In the third line, you get all of the names of the calibration files. You stack the calibration files. You reduce the data using the formula that I showed you earlier, and then you display your final result up here. So that's great. It's a very simple bit of code. This is all there in the tutorials for the package, so you can go take a look at it, but it's relatively simple. We can also do stacking, where essentially these images have to be moved around to sit on top of each other. And only if they sit on top of each other will, we can add them up, because when we have more frames, we get better signal. But of course, naively, you could just stack them on top of each other and you'd get this really ugly thing. And the reason you get this really ugly thing is because even though you have multiple photos of the same region of the sky, there's bad tracking, there's bad alignment, there's bad seeing, and all of these things cause stuff to sort of jiggle about a little bit, so you can't naively add it. Basically, what this means is that the same pixel doesn't correspond to the same point in the sky, right? So what do? You need to find some way of adjusting the pixels so that they all point to the same point in the sky. So one solution is to find the same star in multiple frames and then shift all the frames so that all the stars sit on top of each other, right? And then you add them together. So it's a very simple idea. And for example, this is a page from the Astrolab documentation. There's a little function called find star. It sounds fancy, but basically all it does is it takes an array and then finds the brightest pixel in that array and calls that the star. This is not a very efficient way of doing it. There's a lot of room for improvement. But the basic idea is, and I'd also like to point out that here you can see the little print log that I mentioned earlier, which will display this little image. It'll show you the region within which it's looking for a star. It'll highlight out the little star that's there as well. So what's the workflow? Well, you take a light frame, you reduce the image as I described earlier, you find the star in the image. Now, of course, like I said, there are better algorithms. Maybe we can look for a centroid. Maybe we can do something of that sort. I haven't had the time to do it, but if someone wants to do it, that would be great. Then once you found the star, you find the shifts of the same star across multiple images. And then you shift the image and stack them. So how would this look like in the code? I've just got a little bit of code here again. Same idea as before, load the file names of all the flats, of all the lights, have some arrays, sort of bookkeeping to keep track of this. For each of the files, load the image, reduce the image, find the star. So if you can see over here how it finds the star, there's a little search area that's shown in green. There's a rough position that you put in, and then it looks within this region and finds the actual quote-unquote star. It measures the shifts as the distance from the first. We assume that the first image is the right location. And then we sort of stack it, and we get a result. And you'll notice from this result that there are these little borders at the edge of it. And the reason those borders exist is because the images have been shifted. And so some of the images will not overlap. Some of the regions of the images will not overlap. And this ends up becoming a much better image. So this is just the way in which we process data. So once we have this, you could have red, green, and blue images. You stack them together, and you get a nice color image. And that's the sort of image that we had right at the start. And we don't really have compositing right now, which is adding red, green, and blue together, but that would be a great thing to implement if someone was interested. Yeah, it's also something that I've been thinking about doing for a while now. Good, so that's the first basic example. The second one, which is a slightly more scientific example, is the idea of stellar photometry. And I'm going to talk a little bit about this. And the question really is, can you infer the temperature of a star just by taking a photograph of the star? It seems like, that you're getting a lot more bang for buck than you thought you would. Like, I mean, this is just a photograph of a star, but no, you can actually do a little bit of science with it. So how do we do that? I'm just going to go through very, very quickly, very briefly, the basic ideas of luminosities, magnitudes, and colors. And on the right here, I have basically the zoo of stars from the Hipparcos catalog. I take a bunch of stars and we plot their luminosity, which is the amount of energy that they emit per unit time, and their color, which is how blue or red these stars are. And of course, luminosity is a terrible unit because it's huge. Like the variation is huge. Like Betelgeuse and the sun, there's about 10,000 units between them. So you can't use a linear scale. It makes much more sense to compress everything into a log scale. And this is what we do for hearing. This is what we do for sight, because our senses are logarithmically scaled. So of course, the magnitude scale, which is a standard thing that astronomers use, is a logarithmic scale and compresses these variations into a small region. So that's the difference between so luminosity and magnitude are sort of measuring the same thing. And colors are what we call, unlike the colloquial name, colors are what we call the difference between the magnitudes in two bands. So the x-axis here is the color index, which is the difference between the blue and the green magnitude. So it sort of measures how blue a star is. And it turns out, as you can see from the top and the bottom here, that there is a sort of one-to-one correspondence between the color of a star and its temperature. It's not linear, but there is a little link between them, and that's what we're going to use in this experiment to sort of understand whether we take a photograph of a star and figure out its temperature. And hot stars are bluer, cool stars are redder. So how do we go from pixel values to magnitudes? Well, we take these sensors. These sensors have little pieces of colored glass on top of them, and they only let certain colors through them. So you can take a red image by putting a red filter on top of it. And the goal is that if we have two stars, we take a photograph, you have a target star here and a reference star here. You can then go from the target by knowing the magnitude of the reference star, that's the top right here, you can find the magnitude of the target star. And the idea is to do aperture photometry, where you count the number of photons between the target and reference stars, find their ratio, and do some work with that. I'm going to move a little faster because I'm running out of time, but I'm just going to show you how we do it in Astrolab. And the basic idea is that you locate a star, you crop the image around the star. And what you would expect now is that if this is the hill that the star is, you would expect that as you kept counting in sort of circles around the star, at some point the contribution from the star should go down as it does here. And that eventually the integral of this hill should flatten out. In reality, what happens is that the number seems to increase, and that seems to be a bit of a problem. And the reason for that, however, is because this hill is actually on top of a little plateau. And so as you're integrating out these values, the counts in the background keep increasing because there is a sort of background value there. So one thing would be to remove the background. Now you can do it naively by just sort of plugging in values. I plugged in 100 and that's not high enough. I plugged in 250 and it's low because after a point, it's too high. After a point, it starts dipping down. I plug in a value like 237.5 and it seems sort of right. It's like a little bit of a Goldilocks thing going on here. But what we would ideally want to do is automatically figure out the background. And this is something that we try to explain to undergraduates about this notion of iterative 3 sigma clipping and rejection. But of course, it makes sense if you just explain it as a simple act, which is you scatter little circles around the image, you compute the histogram of the aperture values, and you say, okay, everything that's beyond 3 sigma, ignore, and then repeat the same process again and again. And as you keep repeating it, at some point, you're going to reach a stage where no data points are discarded, which is this point here. And when that happens, you stay here and you say this is okay. So at this point, you're okay. And the end result looks like something like this. So this is something that's done behind the scenes in the Astrolab package, but you can also read through it and see what it does. So you start off by defining a bunch of apertures. And then after auto rejection, you notice that the star has been ignored and only the background values have been taken. So you average out the values within each of these little apertures and you get the background. So this process gives you a target. So you can now take these this process gives you the background values, and using the background values, you can find the counts of the stars. So these are all slightly complicated ideas. But the basic idea to get out of this is that you can find the counts of the star, and from the counts, you can find the magnitudes. All right. And you can find over here, I've shown the difference between the theoretical and measured magnitudes, and they're very close to each other. But now, of course, the real goal is, can we find its temperature? And as I pointed out, the idea is to go from magnitudes to colors, which are the differences between these magnitudes, and then from the colors to the temperatures. And it turns out that the package has this way in which you can give in some magnitudes and it will tell you the temperature of the star. I'm not going into that in detail, but if people have questions, I can talk about it. And the end result is that the measured temperature of the star in this method is 7920 Kelvin. Well, the actual temperature is close to 8,000. And that's an error of less than 1%, so the answer is yes, and it seems to work extremely well in and remember, this is data that we take by just taking a camera and going out with a telescope. You might say, oh, I don't have a telescope. Well, it turns out you don't need to do it with a telescope. You can just do it with a camera. You take a DSLR out, you just put it up on a tripod, you take a photograph or a bunch of photographs. So that's what's over here. It doesn't look very nice, but it's the Pleiades here and Taurus here. And this is DSLR data, which, you can take a raw image, and this is package RawPy, which I use, and RawPy can read the data. And you can repeat exactly the same process here, and you find that there's a less than 2% error by just taking your camera out into them. So the telescope lens is acting like a camera, which again is pretty cool. You can do basic astronomical photometry by just taking out a telescope, by taking out a DSLR or a normal camera out. You need to shoot in RAW to get actual data, which is why a cell phone won't work. So you do need a DSLR, but even a cheap DSLR will work. So that's quite cool. Anyway, so this is the basic thing that I wanted to show, but I just thought I'd just show one slide of some interesting results from another part of the code, which I didn't talk about, which is spectroscopy. And again, I don't expect everyone to understand this, but it is quite cool what we're able to do, because we're pushing the limits of what an amateur can do. So the idea of spectroscopy is to take the light from a star, split it up, see what different components there are in it. And over here, you have two different stars, Betelgeuse and Sirius. And you can see that they have very different features. Sirius shows very clear hydrogen lines. So just this image is proof that a star like Sirius has hydrogen in it, which is quite cool. And this image here is proof that a star like Betelgeuse has titanium oxide in it, because it has the telltale signature of that star. And again, I repeat this again and again, because it really is amazing that I can just do this from my roof with a very, very small telescope. We can also go on to do things with planets. So for example, this is the spectrum of Uranus, and this is, you can actually see when you look at the spectrum that there are these little dark bands. It's maybe a little faint in the image here. But if you actually plot the spectrum out, you see these dips, and all of those dips are methane. And you can just take this data and say, hey, look, Uranus has methane in its atmosphere. And this is, again, data that a first-year undergraduate student can do by just taking it out in the night. But really what pushes it is to calculate the redshift of a quasar. So this is quite cool to be able to actually measure the expansion of the universe, at least at some rate, from a telescope that's out in the night. And so this is the furthest object that an amateur astronomer can see, which is this thing called 3C273. And it takes about 3 hours worth of data. You've got to sit there, calculate its spectrum, take data, etc., etc. And after a lot of painstaking work and stacking the spectrum and doing a lot of work that I've not put down here, you can actually see that this is this guy. And over here, this faint fuzz is the spectrum. And what you'll notice is that there's a small region of the spectrum that's very bright. And if I compare a star like Sirius, which has the Balmer beta line here, and we know somebody told us that this spike here represents the beta line. So the reason that the Balmer beta line is not where we expect it to be is because this galaxy is moving away from us. It's receding at a very high speed. And so you can use the Doppler shift formula to estimate the redshift of the galaxy. And we find the answer to be 0.1577. The actual answer is apparently 0.158, which is, I think that's really, really amazing. So this is the sort of pretty much the most distant object. Maybe there are more, but I haven't found any. But this is really cool that we're doing sort of, sure, not publishable stuff, but really sort of pushing the frontier of amateur astronomy with relatively cheap equipment. I mean, this is not very, very expensive, and an undergraduate college can afford it. So, I mean, there's a lot of room for improvement. I spent too much time on this slide. There's just so many things that can be done. I'm not going to go through all of them, but you could just take a look at it. Maybe I'll share my slides so people can take a look at it. But the basic idea is I would like to include some more metrics for my images. I'd like to do, so right now we've done aperture photometry where we draw these circles around it, but that doesn't work in crowded fields like star clusters, because when you try drawing a circle, you'll catch some other star. So there's another way called PSF photometry, which is something that I want to try and implement. There's better star finding algorithms using cross correlation would be very, very nice to do stacking, sort of automate that. And these are just some of the ideas that I had. And it would also be very nice to have a slightly visual interface, because right now, those dummy positions for stars you have to sort of do manually, but it'd be nice to be able to click somewhere and say, hey, this is the pixel at which we have the dummy location of the star, and do something of that sort. Quick note on acknowledgements. All of this work was done thanks to Professor Dipankar Bhattacharya, who's the head of department at Ashoka, and he's really, he's sort of the driving force behind the astronomy lab, and we designed the lab together. But a lot of this would not have been done without his sort of guidance. Pradeep is our senior lab technician, and he made a lot of the stuff that we use here, which is also very important. The package itself was developed during a summer internship with a bunch of undergraduates. These are the ones who've contributed the most, although there are others. And the data that I'm showing you here has been collected by by everybody, but also by these undergraduate students, Keetana, Isha, and Ronak, who spent a lot of time. Keetana and Ronak spent a lot of time catching the data of the quasar. So yeah, so that's the end of my talk. So I hope you enjoyed it. Yes, so Agria, you asked the question whether the raw mode on one's camera. I have never seen a raw mode on a camera, so I don't know. I would be very curious to try it out. That could be one more of the potential things that works here. It would be excellent if that would work. Do most phones have raw modes on them? Because I've never seen one.
Nowadays they do.
Yeah?
You can go to Pro mode on your camera, and that will allow you to capture raw photos.
Oh, I should take a look. My phone's ancient, but maybe it's there. It would be very interesting. I would be very interested in knowing this. And of course, it has to be sort of compatible with something like RAW5, but I think that should work. That would be fantastic if you could just take your phone out and take a photograph and get something out of it. Any other questions? I'm happy to answer. There are tutorials on the website. You can take a look. It's really simple stuff. But I use it all the time whenever I do my own data processing for astronomy. I do a lot of astrophotography, and my first pass is always through this code. Very happy, definitely. Anyone? Any other questions?
Okay, if you have a question, go ahead.
Yep. So I had this question about because I know that the project was developed for a pedagogical use case.
Mm-hmm.
I was thinking it's more of a question about how people are using the package. Mm-hmm. So I'm assuming as people get to more complex use cases, they do want to just graduate to using other more complex packages.
Yep.
So for example, I have some experience with image processing, and I would, for example, the thing that you mentioned about adding biases for the images, I would use something from Scikit-Image for that. So I would just go to Scikit-Image's restoration API to do some denoising.
Yes,
so
yes.
your students sometimes ask you for tips like that?
So far, no. Remember, these are first years. They're happy to get anything working in the first place, so they're not really that enthusiastic. Occasionally, you do have enthusiastic people. I personally am not a big fan of it. So, if you go through my code, you'll notice that I very rarely import anything beyond NumPy and Matplotlib, because I want to make everything sort of down to earth, because the idea is that it's pedagogic. Of course, these packages exist and they do their work very, very well and very efficiently. But I want people to be able to go back and look through the code that I've written and say, hey, I understand what's going on here. There's very little black box stuff. The code is reasonably well documented and it all uses just arrays. That's why for example, I could have created an image class and have a display, method within it. But I didn't want to do that because I want to make this as close to just manipulating data so that students can understand that intuition behind it. But you're right, of course, it would be fantastic to use these other packages. At one point, we were working with sunspots. Okay, and we used the find star. We sort of inverted the find star algorithm to find the sunspot, because it's like a dip. And then we had to do this sort of thresholding. And now that we can do by hand, but Scikit has, a bunch of very interesting stuff that can be used. But we ended up writing our code by hand because we actually felt we understood it better. So, it's just a pedagogic thing. I mean, just nothing more than that. It's nice to be able to, put constraints on yourself and do something like old-fashioned.
Yes. So just building upon that, I have another question.
Yeah.
So you mentioned that you could have created an image class to handle all image related operations, but you didn't do that. Like, is some part of the motivation behind that also because these are, for example, astrophysics undergraduates and they may not know the concepts of object oriented programming?
Exactly. Completely. And I don't want to get into that, because then they get more focused on the computer science of it and less focused on the actual what are you doing with the data. Because there will be enough time for them to learn all of this later. When you start using AstroPy, which is the sort of standard, like bread and butter of astronomers, you have to know all of these things. And you will eventually learn it. But you shouldn't, I believe that you shouldn't be clouded by all of the fancy jargon. You should actually know what's happening with your data. And that's sort of what I wanted to get across.
Makes a lot of sense. Thanks, Philip.
Not at all. Lots of fun. Thanks for inviting me. Shall I stop sharing? I think I should. Yes.
Do we have time for one more question, Srihari?
Yes, one more question and we can quickly go on to the next one.
Okay. Does anyone have any questions? Otherwise, I'll ask my question. Okay. So this is sort of building up from what Agriye asked you, Philip. Could you tell us a little bit more about your experience working with undergrads on this? And I get your point about physics students or science students spending more time with the data and not having to worry about the actual writing of the code. But did you find that did this help them get into scientific computing? Did you see some of them get interested?
Definitely.
Good.
Yeah, definitely. It was definitely people have gotten very into this, and it's really helped them. And basically, I think it's a trade-off, right? You can't just code by doing hello world. You're going to get really bored eventually. So you want to be able to do something a little fancy, but you also don't just want to import one package and then do something really fancy. So this, I think, is a good middle ground, because you still have to do quite a bit to get there, but you don't need to get bogged down by annoying errors. So for example, the quasar thing was a good example. It was very difficult to actually calculate that. And this particular data was analyzed by me, but we had an undergraduate, a first-year student, who got really enthusiastic about it. And he was sitting around trying to stack, 3 hours worth of data. And, the problem is that it's faint data, so it jiggles about a bit. And you've got to figure out your way to do it. Now, what I think the package has done is it's gotten you to the stage where you can fool around with spectrum data, which normally you would not be able to do, because that would be a huge hill that you'd have to sort of cross. Now, nobody would be able to do that. And if you're going to do that using other software, it'll just stack it for you completely. So, you're not going to learn anything. You're not going to benefit from playing around with the spectrum. So that way, I think that this sits right in the middle. It allows you to get away from some of the annoying stuff, and it allows you to do some of the annoying stuff that's actually interesting. Like to sort of say, oh damn it, I've got 600 images of the spectrum. I need to find a way to align them, and there must be a smart way to do it. It was really cool. I mean, like you saw a little hump, right? And there are a bunch of other humps around it. Now, if you don't stack them just right, those humps disappear. But if you stack them just right, they appear. And it was quite exciting when I saw it for the first time and he saw it for the first time. It's just a nice feeling, and I think that's a feeling that stays with people. So, in that sense, I think it would help with scientific computing in the long run. So I hope I didn't take too long.
Oh, no worries. Thanks a lot for the great talk again, Philip. I think I'll call upon Yuvraj next to present on Python meets the cosmic web, something I've been looking forward to. Yes.
Yeah. So, hey guys. So this talk will be mostly an extension of like what Philip has showed you guys, like what you could work with amateur data. This is like what it takes to move from an amateur data analysis to an actual publication, which is worthy of a master thesis. So yeah, I'll start sharing my screen. All right, so let me talk about the motivation that actually goes behind this presentation today. I hope.
Yuvraj, sorry
Yeah?
to interrupt.
Yeah.
Is it just for me, or was the screen not visible?
This is what I
This is-
mentioned, like when we were testing as well. Is the click to full screen pop up? I don't believe that's intended. Are you sharing the whole screen or just the window?
I think I'm just sharing the window. Maybe I'll just switch it. Yeah.
Yeah, might be.
Is it fine now? I guess so.
You have not shared yet, at least not on my end.
Okay,
Sorry.
cool.
Same for me.
I see it now.
I can see it.
Yes, it's
Works
visible
now?
now.
Yes.
Great. Yes.
Okay, good. Okay, so yeah. So I'm basically talking about my master thesis, which is more on the astrophysical side. I just try to look at how galaxies are aligned with the large scale structures, more specifically the cosmic web. But since it is a gathering where people are interested in understanding like what goes behind in terms of coding and how we tackle real world problems with different techniques and programming, I will also be covering about the programming part as well. The motivation before I talk about all the physics and the programming is that it's just intended to all these undergraduate students who are mostly interested in like trying to go there. This is me with my bachelor friends during 2018. We were all looking for like multiple ways to like figure out how to learn about doing stuff in astrophysics or in programming, and maybe if someone is interested like that, I hope that they benefit from the talk as such, like Phillips or mine. Yeah. So again, as I told you, like since to appreciate the coding that goes behind this problem that I'm dealing with, we'll be covering the background of the problem, which I promise that you don't need a much of a background within the astrophysics part. I'll try to cover as much as you want and whatever you want to know to follow me throughout the slides. And again, how I use publicly available Python libraries and different coding techniques that helps me to quantify the results that I get regarding the galaxy alignment, and also like ensure that it is faster and I can like not just work with a certain set of data, but I can like scale it to multiple data set or even a larger data set. All right. So let's come to the physics part of the talk. So we know three things about galaxies. Like when you just look at galaxies, you have multiple information about them, like the star formation, their color, their morphologies and stuff. But there are three easy things that you could understand just by mere visualization of some spectra or just a galaxy catalog. One would be that the galaxies rotate. All you have to do is just look at a galaxy, and when you look at a galaxy, you can see that there are certain you could also resolve in such a way, thanks to our new telescopes, that you could see even individual particles, like individual entities like stars and quasars from these galaxies, and you could see that when you take a spectroscopic analysis of them, you could see that some of them are red shifted and some of them are blue shifted, and which indicates that they are rotating in such a way. And we also can see that by just looking at the photographic plates of the galaxies, we know that galaxies have different shapes. These are the well-known spiral galaxies and the elliptical galaxies. You can see these beautiful disc-like structures that you could see here. These are the spirals, and ellipticals are usually blobs, like they are like some spherical elliptical mass structures. So yeah, and when you get a lot of galaxies positions in the night sky, and if you just plot them across the night sky, what you could see is that they're all clustered, and then they form this thing called as the large scale structures, which is a pretty cool feature because we usually expect universe to be homogeneous and isotropic, as what we get from the Einstein's equations and the Robertson-Walker metric of our universe. But still, we do find such structures in our local universe. So we are just curious, like why these things usually happen. Now, the question that I put forth in front of you is that, do you think these individual phenomena that you see with galaxies somehow correlated? Well, that is what the most successful theory in to explain why a galaxy spins say so. And this theory, which is known as the tidal talk theory, basically says that uh, you have a galaxy, but before this galaxy becomes galaxy itself, it's called as the protohalo, where it's just dark. There is no stars and anything of such sort, and it's just collapsing together to form the galaxy that we see in our current universe. And you could you could like then explain how individual particles are distributed within this halo, because um, in our universe we have this idea of like I'm really sorry, like if there is a question I can't see it because like I have to come back to the chat.
Oh, no worries about that. I think we can.
Okay, cool. I'm sorry. Yeah.
Yeah, don't worry.
Okay, so we have this idea that everything in the universe starts from the smallest structure, and then they merge together to become the larger structures of our universe. So you could say that when I say here it's the inertial tensor of a protohalo, you could just assume that it just explains how matter is distributed within this protohalo, which is gonna convert into a galaxy. And when this protohalo gets experienced gravitational force, mostly by entities that are nearby to it, like it could be other protohalos or different larger structures or something, each particles inside this protohalo starts experiencing a gravitational pull. But since they are not evenly distributed and it's not like a point source, each particle has like a differential force which induces a torque, and this torque is directly related to how disoriented is your actual distribution of this matter in this protohalo with respect to the local gravitational field, and that results in the protohalo gaining this angular momentum. It starts to rotate, and when it is rotating, then a lot of physical processes happen inside. They start forming stars and stuff, so they cool down and they have even more capacity to clump and become a more compact object. And when they become compact enough that the external angle, the tidal shear fields can no longer be imparted due to the gravitational impact, because the more compact it becomes, uh, the differential forces become smaller and smaller. So they just retain their initial angular momentum, whatever they had, and they just retain the initial spin that they gained. Now the question is that is it possible that galaxies still retain these rotations, like whatever we expect from this theory? Can we still see them there, or is there some kind of other physical processes like merger events or like some other weird physics that comes into their case that which makes us like not expect the same, or like they have changed their angular momentum? So if it was really hard for you to guys to follow it, this is basically a visual representation of how it actually goes. So like it rotates, and then you find that this is the direction in which the galaxy rotates. So we have some theoretical predictions regarding tidal talk theory. But before that, let's talk about the large-scale structures of the universe. So we know that you just saw in the previous slides that galaxies cluster and they form these large-scale structures. But just by mere visualizations, we can like create 4 subtypes. So these are called as the knots or the clusters where all these matters clump together and they make these knot kind of things. And then there are these filaments. These are these thin lines that you could see here. So these connect these kinds of knots. So filaments are like these threads that connects the knots, and hence the name, the knots and the filaments. And you have the cosmic sheets. These are like structures that are similar to filaments, but they are flat. So they have a two-dimensional structure. Like they are not a thin strand, but they are like a wall that happens between these galaxy clusters. And finally, we have the most famous voids. These are regions where matter move away from everything. So the sheets are the regions that cover the void. It's like those thin membrane that covers the void, and then filaments are like those extra lines that connect the clusters, and this is what we see with our large scale structure by mere visualization. But the thing is, when you go for a mere visualization aspects or something, you could, what I could see as a filament could be a sheet for some other person. So you need some solid mathematical construct to do all these kinds of classifications. So that's where these terms called as the eigenvector comes in. Eigenvector is basically an entity or like a construct that we talk with shear fields and how tidal fields work. But for the sake of easiness, I can just say that these basically gives you the directions in which matter collapses. So you have a threshold value for the eigenvalues, which are the values that are associated with these eigenvectors, which indicates the direction in which you see collapse, or an expansion of like distribution of matter. And if everything is collapsing here, you can call those regions as knot. And if there is only one freedom of elongation or stretching with respect to all these 3 eigenvectors, you can call those regions as filaments. Then sheets would be regions where you have like 2 axes of freedom of expression to expand, and voids would be the region where everything moves away from each other. From the theoretical predictions, we have 2 key ideas. The major idea that we get is that the galaxies are not expected to be aligned along this even direction, which is known as the axis of the fastest collapse. So this means that to visually understand this, the galaxies are now expected to be aligned along the E2 or the E3 plane, which is the sheets, which is given by the plane of the sheets. So if you have a sheet of this sort, the galaxies are now expected to be rotating along this side. Or you have this filaments, which are like the spines of the filaments, which is given by the E3 direction. And if you have a galaxy, and they are expected to rotate along the spines of the filament. So their spin normals are pointing towards the same direction. The next prediction is that the next step was that just by relying on mere theoretical works, we went for actual cosmological simulations. These are like n-body hydro simulation construction works that tries to like reconstruct our whole local universe by implementing all the cosmological parameters, and we have a key prediction from them. The galaxies are now expected to be aligned along the spines of the filament more than the sheets that we saw in the previous slides. And the more massive the halos are, they have a tendency to flip their spin normals and become perpendicular to the spine. So if you have a spine here, and then these galaxies can flip their spin normals if they are more massive. This is particularly interesting because like elliptical galaxies, which when we look at our observations, are usually more hosted by a massive halo. And now they are expected to show a perpendicular alignment, that they are expected to rotate perpendicular to the spine of the filaments, whereas the spirals are now expected to aligned along the spines a spine of the filament that we see in our large scale structures. Now the question is like, how do we actually verify these claims? Like you saw that in simulations, you saw that in theoretical work, but they retain their prediction, or like they become valid when we actually see it with actual observations. So that's when the programming aspect, and also like how we could utilize various physical modeling that we know about these galaxies come into play. And we could even extend mere observational stuff into a statistical study that gives you some solid concrete idea like how things work. So for this, we need a galaxy catalog, a bunch of galaxies that has all the necessary information that you need to calculate the spin normals, again, which is the direction in which they rotate. And you also need uh, something of a filament identification method, because when you look at galaxies, again, if you recall from the previous slides of the large scale structures, they're just randomly distributed. You need some mathematical construct to actually infer that certain galaxies form a filament line or some sort of things. So there are multiple methodologies that you could use, but we need something which is solid and which can be easily obtained or like used on observational data that we get from galaxy surveys of, like, say, larger telescopes that we have in the sky, like Hubble, James Webb Telescope and stuff, and we could utilize it. So let's start with the actual galaxies. So if you do things properly, it basically looks like this. Those black lines that you see here are the filaments, and then the red dots over here are the galaxies. And these are the spin normals. The green quivers are the spin normals that you could see. And you could see, like, this is what is the background. Like, all you have to do is take a dot product between the spine and the filament normal, and that gives you the basic idea, like how is tidal talk theory still valid, or do we have it differed from what we anticipate from us? You have to move along the equator to go to reach to the bottom of the object that you're looking at, and you look at what is the height that you have to go, which is the declination, or like how much you have to move from here. Anyway, it's the same. And when you look at this thing, how much is the plane of this galaxy that you're looking at makes an angle with respect to the northern the north celestial pole of our observation. But before doing this, it is also important that we need to first find how far are these galaxies, because which is very important to find out which is the closest point for the filaments. Like, you have this filament, and if you can't put if you can't put the galaxies with next to the filament points, you can't find out which is the closest filament. Then you can't do the dot product of whatever we are intending to do. So to do that, what we could do is that with just the right ascension, declination, and the redshift of the galaxy, you can just calculate how far is the galaxies from an equatorial setup, which is based on our Earth, which is not really applicable or helpful for us, because we are moving around the center of our galaxy. So we need to transfer it from our frame of reference to the galactic frame of reference, which is the center of the our Milky Way galaxy. So to do that, I utilize this small simple code where I just call, I have this Python module called as the Astropy, which is a well-known astrophysics Python module that helps you to do all this sort of analysis. And I just have to, it's all 5 lines of code, what you see here right now. But what exactly goes behind is this a whole set of thing called as the spherical trigonometry, where you have to find out the location of the galaxy with your frame of reference, and you have to flip it to the actual galactic center, which is very hard. But what was really hard for us in terms of mathematical calculations have been really simplified with just 5 lines of code. And all I need to do is like prepare an array for the galaxies with all the required values, which is the right ascension, declination, and the redshift of the galaxy. And all I have to do is just run all of them, and I get the positions of these galaxies, which is cool and fun for me. So if you are interested, you could have a look at the Astrolab Python module. Now, given that we know where is the actual galaxy there, now we need to calculate the spin normals. Again, when you calculate the spin normals, it is going to be something that you express the vector, the spin normal, in your frame of reference, which is the equatorial coordinates. So from the equatorial coordinates, you have this kind of equations where the theta here is it's dependent on the declination that you have here, and again the right ascension. I don't want to go into the nitty-gritties of the work because it's there is a reason why it's tedious and why we have all these Python laboratories like modules to ease our work. So where here this R is called as the it's the component which is dependent on the term here I, which is the inclination angle. So this inclination angle is something that gives you an idea like how inclined is the actual galactic plane from your field of vision, which is this is really hard to calculate because like for actual like what you see in actual observations of these galaxies are mere photons, right? So it's really hard to pre-process all of them and do and calculate the exact inclination angle. So what we do is that we go for something which is a module this is like a modeling that has been given to us by astronomers way early, and this is a paper from 1989. So we just utilize this model where it takes the b by a ratio, which is the ratio of the minor axis by the major axis, and using this value followed by this parameter that you have for different classifications of galaxies, you can then get the inclination angle, which would then give you the actual spin normals in the equatorial coordinate. So once you get it in the equatorial coordinate, you have to convert it into the galactic coordinates. Again, the same thing that we did for the positions of the galaxies. Again, so to do this, you need a 3 by 3 rotation matrix that is again given by a paper also in 1989. But the problem is that doing it again is a very tedious process because it involves spherical trigonometry. So you could just simplify it by a mere line of code. So this is again like a Python library that is constructed similar to what Philip has told you about AstroTools. So Astrolab. So here this is AstroTool, which has such cool functions of like transforming your vectors across various regions. So you don't have to do this spherical trigonometry conversions manually, which sometimes can be error prone. So with this, you get the spin normals of the galaxies. And it's what it took as pages of algebras that you saw in the previous slides is now compact in some small code snippets, which I find it to be personally great. Now, coming to the filaments. Now, how do we actually compute the spines of the filaments? This is something that I haven't been actually involved, but one of my supervisors actually worked with actual observations of the galaxies, and he worked on it. So you have like this galaxy distribution from your large scale surveys of the night sky. You get the positions of the galaxies in your night sky. The goal is that in order for us to reconstruct filaments, you just have to fit cylinders across these points or the galaxies that you see here. And that is all you do. And once you get these cylinders, you can call these structures to be filaments with which you can do your analysis that I've been talking so far. But there should be some kind of regulation that ensures that there is like a rule that determines how these cylinders are fit on top of these data points or the galaxies. So these are these two data energies that we assume. One is that the data energy that tries to ensure that the distribution of these filaments, like how you fit these filaments on these actual galaxies, ensures that it resembles the actual galaxy distribution, and it shouldn't like make some any sort of connections on its own. And the second thing is that we have this interaction energy that tries to ensure that the galaxies are connected in a smooth way, that you don't have any sort of ridges, or like you don't have any sharp turns as such, or it's just a smooth connection. Because according to our explanation of what a filament is, filaments are something that is smooth, that easily connects to galaxy nodes. So if
Hi,
you
Raj.
yeah,
Sorry to interrupt. There's close to about 2.5 minutes left. 2 minutes,
okay,
40
cool.
seconds.
Okay,
Yeah,
cool.
just one.
So all you have to do is, like, if you try to do this analysis, then you would get like a cool feature. You could just let it run again and again as in Markov chain Monte Carlo realizations, and you could see that you get these cool lines that you can see here. Great. Um, so once you get your galaxies, the spin normals of the galaxies and the spines of the filament, all you have to do is like find the nearest filament points, like the points that you see here with the galaxies, and you take a dot product between the spine of the filament. This is a classic n into m problem, where you have like multiple data points, and doing it all together in a brute force method would be really hard. So what I do is that this code tries is that it splits the actual filament distribution points into smaller grids. So when we know the x, y, z coordinates in the supergalactic plane of the galaxies, we just go to the particular point that is there, like just the particular grid that we have constructed for it. So that reduces like looking at all these galaxies just within this particular set that you have here. So it's just the actual thing actually takes like if I use the grid, it just takes 36 seconds for me to complete, whereas if I don't, it takes more than like say 20 minutes or something for me to do this actual process, which is a cool way to see how programming helps us to do large scale data analysis. So once you get these dot products, you take, which is the dot products are nothing but the cosine of the angle between the spin normals and the spine of the filament. And you can have three cases. One is that if there is an alignment, you would see that a lot of galaxies tend to have the cosine value of their angle closer to 1. So you would find a curve just like this. Or if it is an anti-alignment, you would tend to have more dot products that have values closer to 0. So you would have something like this. And the null hypothesis is that there is no expectation of any sort of alignments with respect to the spines of the filament. So it would be just like a random distribution, which is a plain histogram, a unity histogram around that you could see here. Now, how do we quantify these results? Because what we get here could be just a random event, but we need to ensure that whatever we get here has some statistical significance. So to do that, I have this thing called as the alignment signal significance, where I create 10,000 mock samples of these actual galaxies that you see here. I just retain their positions, but I change their position angle, which is the inclination of this galactic plane that you see, which can give us a completely variety of alignment trend. And I just utilize all these 10,000 realizations. I take the dot products between them, and I construct this 1 sigma bar with which you could do this. You can compare and see like how significant is actually your result, given that it's not some kind of a random event. So yeah, so I just find the difference between the expected null hypothesis and the actual significance, like actual signal that you see, and then I just divide it by the standard deviation that you obtain from this 10,000 events. Followed by that, I also have another way of quantifying the signals, which is like from those 10,000 cases that you had from the previous, the 10,000 cases that you created for the mock observations, I take their mean and then I create this distribution of their means, which gives us the actual distribution of what it actually how the null hypothesis work. And I see how the mean of the actual dot products, which is the actual signal that I get, I sum them up and I get the mean, and I see how is this mean deviating from how many sigmas is the mean is from the mean that I get from this null hypothesis cases. So if it is on the right hand side, it means it's aligned, and if it is on the left hand side, it's anti-aligned, and if it's closely here, then it's just random alignment. And I also do the KS test, the p-value, which ensures that the smaller the p-value, it says that these actual signal and the null hypothesis are not from the same source, but it has some sort of significance. Yeah, like the thing is that when I do all this in terms of vectorized math, like when I make them into arrays and all sorts, when I handle them as numpy arrays, rather than like me doing all this 10,000 cases all at once, it is really fast for me to ensure that I complete all this analysis in a faster way, and it also ensures that I don't have to pre-compute predefined values like the right ascension and declination and the cosine and the sine angle. So this is a sort of how the code works. And
Yuvraj, just sorry for the second interruption. The time's over,
yeah,
so just might want to wrap it up.
yeah. So these are the results that you can see here, and you could see that the ellipticals show a strong anti-alignment, whereas the spirals show a faint hint of alignment. The next step was that to find out, like we found out that the 0.5 to 1 megaparsec region, which is the actual regions where the peripheral regions of the filaments, you find the maximum significance of these galaxies to be around this region, which is an interesting region to look upon in upcoming studies. To ensure that we maximize the hint of the spiral that you see here, like to maximize the signal, the significance that you hit here, which is very small compared in both the cases, we try to ensure that we had a SciPy, a scikit optimizer, which is a Bayesian optimizer that runs through the parameter space and tries to find out which is the best fit of parameters that maximizes these two significance metrics that I have mentioned you here. And we find that these are the regions where you have the maximum alignment of the galaxies. So yeah, thank you.
Right. Just to be mindful of everyone's time, I think starting the next talk soon would be just better. If there are any questions, I think feel free to reach out to Viraj right now on chat or maybe on his socials as well. But yeah, I would like to call upon Vivekanand to get started with next for Python.
I hope I am audible to you all.
Yes.
Yeah, great. So yeah, how much time do I have right now?
The talk is for 30 minutes. I think hopefully we can wrap it by 4:10. So
Okay, great. Okay,
right,
fine.
4:10, yeah.
Yeah, okay. Okay. Let me share my screen. Mm. Is my screen visible to you all?
Yes.
Yeah, okay. So first of all, I just wanted to tell about myself a little bit. So I'm just a freelancer right now. So I was
I just wanted to ask if the uh, voice drop is just for me or for
It's
others.
for me as well.
Me as
It's for
well.
me as well.
Let's wait for 1 minute. Vivek, if you're hearing us, we can't hear you.
think I'll ping him on uh, another social as well.
Okay, am I audible right now?
Yes.
Yes.
Okay, thanks, guys. Like, okay, is my screen still visible to you?
The
Yes.
screen appears blank though. Is it just me or
I can see it. What about
I can see
others?
the slides as well.
okay? That might be me. Sorry. Carry on, Vivek, sir.
Yeah, okay. Okay. Good. Okay, great. So I just wanted to talk about like I don't know how this fits perfectly for the scientific community, but it certainly fits for a lot of use cases actually. So next is maybe I just due to the kind of time constraints, I just maybe I can just freely talk about things instead of just purely following the slides. So basically okay, just wait. Okay, yeah, like, you can see my screen. So basically the thing is like Nix is kind of like it started as a basic language package manager and these kind of things, but then somehow it grew into a much more vast ecosystem. It's not just for it's not just tied to any particular community, but it's kind of like a paradigm shift actually. So the whole world actually do now follow a lot of paradigms like imperative, object-oriented programming, and these kind of things, right? So Nix is kind of yeah simple. Um, not to be not to said as simple, but it's kind of like a different paradigm for the whole way that like even from deployment shells or whatever it is. So it's kind of like a new paradigm of thinking, you could say. Like it just rebases every stuff out there. Mm, okay, maybe I'll just stop scanning the screen, reshare the screen.
That works.
Okay, let me just reshare the screen. Okay, is it visible to you on the screen right now?
It is visible now. Yes.
Yeah,
Yes.
okay, great. Okay, great.
Yeah.
So yeah,
Thanks.
uh, let me just start with this. Like, we all have this some kind of problems with our current computer science, whatever the IT industry could be. Like, we have we are trying to solve certain things over the years, over the decades, and everything. But still, we are stuck at some things like the way. Basically, let's say like we'll have a script-like format. So maybe you need some kind of projects, dependency, software, and everything. This is much more towards this technical side of the talk, actually instead of something related to the scientific thing. So yeah, that's it. Just a heads up. So as you can see, like we have trying to solve things by like either virtual machines, Docker, and these kind of things. Like but still somehow, if you are trying to deploy some web apps or something like that, let's say you have some projects right now. Maybe it could be in Linux or it could be Linux or Mac or whatever it is. So let's assume you have some kind of Python version. Let's start with this example right now. Um, the slides are just for the reference. So let's say you have your Python version right now. Let's say you have Python 3.8 or something. And what if you want to test some particular file, like let's say some particular project file? So what if you want to test that particular project file using some other different Python versions actually? So basically, you might be there are a few possible ways actually. So maybe like purely purging out the Python 3.8 and just installing Python 3.9 or something, and then just write the Python space main.py or whatever the command you use to run the program or something like that. So it's just one way of doing things right now. The simple way to isolate things could be to have a Docker file or something like that. You can do your Docker fetch something like Python, what are the slim version or something like that, and then just run a simple command. But it's kind of like a overhead and overkill for simple basic scripting kind of purposes. So there are too many things about to talk about next, but I just stick to the Python specific things. Okay, so see, this is what we are facing right now, even in the world of computing right now. Like there are ways to mitigate the problems. Let's say you have some kind of you all people know, right? Like in Python, we do not install all the dependencies globally because specific projects might require specific kind of versions, right? So instead, we used to maybe use PyProject.toml or just to do a basic any basic build script or something like that. You might be having some of your own way of doing adapting. There's UV package manager right now. So these kind this kind of the VNV actually the virtual environment actually tries to solve these things by maybe like say installing dependencies into a particular project specific folder actually. So you will have a requirements.txt file and then just install the dependency like pip requirements hyphen or and these things like. So basically, you have solved these problems within Python actually. That's a great achievement actually. So even the modern package managers like UV and all, they're trying to simplify the process actually. So it's like they have all those dependencies installed globally, but not available on the path. Path is something like you will be like exposing in the terminal. So instead of installing everything on the path, they will just install everything in some of their own like own folders. And then when you have some projects like you have some kind of records like NumPy, SciPy or something like that, they'll just fetch dependencies from there and just start the virtual environment inside there. So it's kind of like how UV and all these modern like UV, PIP and all these things have solved little bit of things. But what if you're like let's say I have something like you want to show something like something related to SciPy or something. So you want to deploy a website actually. So that time you have more than Python actually there. You have something like JavaScript and something. Your backend could be in written in Node.js or something, and only your scientific computed part could be in Python. So only within Python we have solved this dependencies problems actually uh, through through PIP, UV, and these things. But for your whole ecosystem, for Node you will be having something like the packages.json something like that. So even every particular ecosystem have their own way of doing things, their own way of solving things. But there's no such thing as like a universal thing which we could do solve all these kind of problems. So that's where actually Nix comes in. So Nix is kind of like a very simple, beautiful, yeah, very beautiful solution actually to all these modern problems. I'm just today's restricting myself towards the package manager kind of thing. But generally, Nix solves a lot of things like it cuts the overhead of Docker, virtual machines, and all these things. So Nix is kind of like it's a language package manager. It's an OS. It's a Linux distribution. It's an original distribution, not based on Debian or something like that. It's an original distribution. Uh, they have their own Terraform kind of thing. It's called Terranix, and instead of Kubernetes, they have something called as Kubinix. Uh, so there are a lot of things going on in the ecosystem. Like it's just scaling out rapidly right now. So yeah, also, what this actually Nick's trying to say is you have something like requirements.txt or something like that. So what you have done is you have declared all your dependencies into a particular file. So no matter how you run it, it will always work. So that's how simply we have solved the problems using virtual VNVs. But as I said, more the complex the project grows and maybe a vast kind of ecosystems. it will be hard to tinker everything into a single maintenance of projects. Like say you will be having some script to activate the Python specific via virtual envs, and then you start installing the packages using Node packages or JSON and these things. So Nix is kind of like an automation, but more than automation, it's more good to say as a declarative paradigm, declarative and purely functional paradigms. So let me just quickly show some slides. So imagine giving the same ingredients and repeat through many cubes or something like that. You'll obviously get some particular tastes in food. The food taste will be obviously different. So that's kind of like a pain in the ass for the whole IT thing. So, but we have accustomed to these behavior. Yes, like let's say if something is not working in your computer, so let's say you have some kind of programs. So your organizations might be like a am I audible?
Yes, Vivek.
Yeah, okay, great. So let's say these days you'll be having some kind of restrictions over which what packages you are installing in your in your corporate systems, right? So you are not allowed to do certain things. So let me just start with maybe about the different health things. So currently some things might be working on your computer but not on others' computer. There are some reasons for that. Let's say your organization might be restricting to not install some games or something like that in your work PC, because let's say you have some kind of Python versions or something like that 3.8 or something. So and then you install some kind of game, and the game's dependency could be Python 3.10. So what usual package managers, the every existing package manager does is it will replace the Python 3.8 with with a new version. So somehow your project actually works on 3.10. It's great and everything. So you start working on other features and everything, all these programming things. But after some point, when you share the code to some other person, it might not work because she's like sorry, his or her Python version could be something different. So UV actually solves these things. Like you have the option to mention which Python version you have to run these programs. But they said the cross ecosystem compatibility is not that good actually. So yeah, okay, all these things. This is what I was talking about, like the dependency hell. So this is what's called as dependency hell actually. So you have now ways to manage the Python specific dependencies, but not a whole thing, not as a whole ecosystem kind of thing, like a cross ecosystem solution. So yeah, somehow the VMs actually solve this issue. So maybe in olden days you will be having something like VPS, like a dedicated server for you, and then all these VPS and dedicated servers you will be using to deploy softwares. But then due to the overhead and the limitations, the containers came actually. Container is is exactly like a VM, but without much overhead. It does not virtualize all these harder things, just only the kernel level things. So it reuses the kernel and everything. So containers somehow solve these things, but all this Docker file and everything. Okay, okay. Somehow it solved a lot of things, but still it's not the perfect thing. Maybe for you to say the example, let's say you have a Docker file, and then you have a Docker registry. So with the Docker file, you will create some kind of image. And then it's kind of like a snapshot. The image is kind of like a snapshot. And then you push it to some registry. And then for deployments, you will fetch the image from the registry and then start deploying. So why do we need that particular image actually? So if we can reproduce the same file from this Docker file, there's no need for this particular registry. But Docker file isn't reproducible always actually. So if you run the same Docker file after 2 to 3 years, it will not work the same actually. There are a lot of reasons, like maybe the package manager it uses might be outdated. It might have removed few dependencies, and it might have flagged something as broken or something like that. And they might be restricting, the whole repo might be gone, or whatever it could be. So yeah, it's kind of like a broken system we have right now. But what we have, what everyone is doing right now is okay, yeah. So what everyone is doing right now is like kind of patching everything on stuff. but not actually solving the stuff. So yeah, within the time constraint, I have to move faster. Okay, maybe you could use see the slides for reference, but yeah. So one of the solutions is to be declarative actually. So let me just quickly show you. These are some of the few advantages if you make something as a code. So it could be portable easily. Like it's kind of like a Docker file, but it's actually better. It's atomic. Atomic means either it's kind of like runs under the parity. Either something runs or something not. So and it's obviously reproducible and all these track changes and everything. So yeah. Um, So yeah, as I said, Nix is a lot of things, but basically you don't have to learn the Nix language to use Nix actually. So Nix you can use in Linux, Mac, and in Windows you will be you can use it under the WSL Windows Subsystem Linux. So it's natively supported in Mac too actually. So yeah, Nix is kind of like trying to produce an artifact. The artifact could be either shells. Shells, what I mean here is like the virtual environment, VNV, all these as packages, package managers, and all these things, containers, VS, and everything. Today we will just yeah, it's not tied to any single ecosystem. It's kind of like a universal build system, and also a universal ecosystem management kind of thing. So yeah, you don't have to learn the next language, but let me just quickly maybe show you some example. So like I said, usually when you install some game or something, it might override the existing dependencies in your computer. Next, what happens is it actually creates a specific, let's say you have 3.8 already in your computer. When you install 3.9 using Nix actually stores it specifically in a particular location. It's called a Nix store actually. It's immutable so that you can't change like to avoid the attack surface actually. So it kind of goes under your read-only file system. When you create a new shell or something like that, what Nix does is uh, while saving, Nix actually uses a particular kind of hash systems. So that everything, let's say you have a Python 3.9, and then you compile the Python 3.9 with some other compilers, some other experimental compiler or something like that. Both these projects can coexist in a system actually. It's not usually possible in any other systems actually, any other Linux distributions or any other thing. So there are ways to do, but like the containerization, all these things, but not a simple way to do things. Nix kind of like simplifies all these things, all this hashing, sync and all these things. So yeah, yeah, and also it's a very good build system actually. Have you heard of maybe like Bazel build system? So when you build a packages or when you build a program, something like that, Bazel is a very good thing. But Nix is kind of like a super good alternative for the Bazel actually. So as I said, Nix is a lot of things. It's also a very good build systems. You could build a text file or OS, music, whatever it is, you can do it. And also it's kind of like have the a largest package repository actually. So Nix is much more. Actually, the next good thing is Arch user repertory. Actually, the A or if you have used my previous distro was Arch Linux actually. So when I was using Arch Linux, I had all these latest fresh packages. But when I moved to NextOS, I got much more fresh packages and all a huge packages actually. So let me just quickly show you like so maybe I could go to some site like this. So it have literally 1.2 million packages actually. So all these packages are made by communities. So maybe you don't understand this. Let me just quickly go through the slides and then uh, yeah, okay. Okay, guys, maybe I can start showing this actually. Okay, let me just quickly show you this. Okay. Okay, I have this particular project. Let me just show you this. I have this very simple program which just prints the current Python version. Okay. What I do is uh, Okay. I am opening my shell right now in this particular program. So usually you'll be doing like Python space main.py, right? So currently I have no Python in my computer. Like how you don't install a particular program for as a global dependencies. Let's say you have some kind of libraries like NumPy or something like that. You'll be installing using virtually env UV or something like that, right? So just like that, I'll be using Nix. Sorry, I'll be installing Python not as a global package manager. There are few ways to do it, but to avoid the Nix complexities, I'll just maybe just show you a very simple way to do it. Um, See, this is just a very simple command. So what I do is I'm just creating a new shell with a package name called Python 312. So it will create a very temporary shell for me right now. So let's say I have sorry, Python space main.py. So when I run this, I'm getting this package. But if I exit this shell and run the same python.space.py, I don't have the Python with me right now. So what happened here is I temporarily enabled the shell actually. I temporarily installed the shell and activated it to my path actually. So maybe if I show you like maybe I can show you like this, like Python 3.3. So let's say I want Python 3.13 version actually. So it just created the same Python version for me. When I ran this, you can see that clearly see the Python 3.13 version here. So just like that, I just installed two Python versions without actually, sorry, I just tried two Python versions without actually installing in my computer actually. So what this actually create is, let's say you have a very large project or something like that, and you want to have a, particular compatibility scenario, like it's just a one out of a thousands of use cases with Nix actually. So just to say, like, let's say you have a program and you want to check, you want to write a script or something like that. Like, so let's say you want to check it with like from Python 14 to Python 3.9 or 10 versions. So you want to check it for all the four versions or something. So it's really, really not an easy way to do it with Docker without the overhead things. You'll be needing some little more RAM or something like that. But here, I can just do it like this. Okay, let me just before this I can just show you that I don't have Python right now. So if I run the which Python, it will just show me nothing actually. But if I enter some version Python 3.3 and just type which Python, I'll get, you can see this. Usually it will show some other path in other Linux distributions, but with Nix actually, Nix you can also use in Nix in Mac or something like that. You can totally replace all your home brew things actually, all your brew file managers, package managing. So it actually the Python here is actually this name actually. This is the name of the thing. Some hash hyphen the package name actually, package name and versions. So this is how the formatting. This is how this hash is how Nix actually differs things between versions. So you can customize your a particular Python version or something like that with this thing. So let me just sorry, yeah, I'm still in Bash. Okay, okay, great. I can have this particular flag right now command. So what this one does is it will create a temporary main shell for me with a package called Python 313 and run a command and then just exit the particular shell right now. So it's kind of like a Docker without the overhead. All happens within a few seconds actually. See, that's how fast it is actually to do things. So let's say I want to check the same program. Let's say it's a complex program. I want to the same program with Python 3.312. And yeah, just like that, it just happened to work that way, that easily actually. It's nearly very hard to do it in Docker actually. So now you might be asking like I don't have a simple project where I have only the Python version right now. I have all these other dependencies like NumPy or something like that. That's why I have showed this particular package here. let's say you have a NumPy, you will be having that package in this particular Python version. Uh, so you will be having some kind of this like this actually.
Hey Vivek, sorry to interrupt. Last two
Yeah,
minutes, if you could
yeah.
start.
Right. Yeah. So yeah, you can do something like this actually. You can do something like this, or maybe like and it will just fetch the packages, build the shell temporarily, and then run the command and exit the shell. It all happens within a second. Imagine how easy it would be like to add these things in the scripting. Let's say you have a script right now with you, and you want to run some kind of scripts with maybe to install a particular Python version or particular some kind of Node version or something like that. All these difference, all these packages, all the differences could be added to just this flag actually, hyphen p flag. So it will just fetch all these things is as easy as this without the overhead of the Docker actually. So now we are actually inside the program and we have just executed the Python 3.11.4 in here. So it just created the shell. On first invocation, it took some time to fetch the packages. On the second invocation, it's just very it's instantaneous, almost instantaneous right now. So it just runs the package and finishes everything. Sorry, my CPU is so peaking for a long time due to which like don't have our hardware accelerations. That's why I think it took more than a few seconds, 4 seconds actually. Actually, it's very instantaneous. So like this, you can check. You can break out of the VNV. So let's say you have a sorry for just one more minute. Maybe let's say I want to run this program with a particular bash version. Let's say the bash will invocate all this Python version or something like that. So I can just say something like bash hyphen c. Uh, Maybe I'm giving the right command, I guess. So yeah, what this does is I don't even need bash to have. Okay, sorry, I gave the okay, I gave the space before this. Sorry. Okay. So what this actually does is I don't even have no don't even have to rely on a bash shell actually. You might be having ZSH actually, ZSH. So let's say you have some kind of script like maybe something .sh, and then you can call using the bash script. You can actually call this. It's kind of opens up some infinite possibilities right now. Right now, it's creating a bash shell with bash and all these things. And then inside this particular shell, we are using that particular bash and inside that bash, we are using it to call a particular Python program. Imagine the possibilities you have right now, like without all this overhead of the Docker. It's actually pretty easy to start using Next actually. So yeah, just lost 30 seconds, maybe like to just show the potentials here. So just like how I install the packages, all these are temporary. Nothing is installed in your computer permanently, like in either packages. So all these are very ad hoc things actually. So let's say I have something like I want to try a package called Spouse. I just pipe it something like this. So just the app can run only once without ever existing in the computer. So there are cool ways to do these things. The other things I told like there are next way to do things like purely within the next language for a complex package dependencies. Let's say I have you can see something like this. You can say something. Okay, you can see it here like all the packages. I can add all the packages here and then invoke it inside my shell and then run a shell hook or something like that. And then call out a particular command or something. It's kind of get complex over the time. But for simple use cases, you can actually do it as simple as this. Right now, we just created a particular shell and just did this same command and same command. You can also try it the same with fish or whatever shell you want. You have some kind of script, and inside the script you might be calling the Python main.py, or let's say you have some other coverages. All this infrastructure and everything. See, it just happened almost like took a little bit of 11 seconds. It's a very old PC. I have very old PC right now, so it could be almost instantaneous. This makes things easier for like setting up things, trying out things, let's say you want to try out something like a particular library or something like that, without going all the overheads with VNVs or something like that, you can do it easily. You can have any kind of packages here. Almost the 1.2 million packages have almost everything. So yeah, I think that's all. We can bind up, I guess. So yeah, there are a few other ways to do scripting and all the things. You can just refer the PPT maybe. So any doubts you have, maybe I can have 1 or 2 minutes, maybe at least 1 minute.
Thanks, Vivek. I think we do have time for one question, and then we'll have
Okay, okay.
5 minutes for conclusions.
Yeah, okay, great.
Srihari has a question in the chat.
Yes, Vivek, I just
Okay,
posted it on chat, so if you can tap, yeah.
okay, that's correct. Okay, I just see it on my phone.
Oh, so the question was basically when you were showcasing the demo on your terminal and you used the command which Python, it had like a
Yeah,
small
yeah,
hash.
yeah, 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 yeah.
Right.
Just like you asked, the which Python actually shows always the same place. That's what I mentioned first about. Nix actually
Yes.
stores something inside the Nix store actually. So whenever I create some kind of packages, Nix actually doesn't store it globally like other package managers. So when I have some kind of packages, it will be but it will be assigned to a particular hash node. So this hash doesn't mean like now we have a clear distinction like Python 3.11 and Python 3.12. The naming actually differs. But what if you have a Python 3.11 and a Python 3.11 with just the JWT compiler? So that time the same name points to the same program, but both programs are different, right? So these things can coexist within Nix actually. So that's how it's easy actually. So which Python points out do this actually for Python 3.11. Okay. So yeah, maybe the hash is something to make a project completely unique. So you might be having a particular flag for compiling a certain Python version. So it
Right.
could be having a very different thing. Yeah.
Got it. Sure. Thanks. That's the clarification I wanted. Thanks.
Okay. Yeah. Yeah. I can see the different hashes between these two things.
I think we have another person who has raised his hand, so feel free to unmute and ask your question. I think just one more question and I think we'll wrap it up.
Yeah. Okay.
I think they have their hand up for a
Oh,
previous issue, so maybe we can move on.
got it. Agria, would you like to take it up? Take it forward.
Sure. Yeah. So
Yeah.
this concludes our third community call, and I would just like to thank you all for joining. It's been great to have you here. Of course, like we discussed, 4 talks, one lightning talk, 3 full-length talks with an astrophysics flavor this time, and thanks for joining. We do have a feedback form that we would like you to fill. Obviously, there's no compulsion to fill it, but if it helps us plan the next community calls and just make them, it helps us make them better for everyone. So please take like 30 seconds to fill this out. It would be amazing. Besides that, I don't think we have anything else. The next call should be on the 6th of December. So we do it on the first Saturday of every month. And eventually, we are thinking of making these, as Srihari mentioned at the very start of the call, we are thinking of pivoting to offline events and eventually a conference if we gauge that there's enough interest in the community. So if you do have
I think
with
he got.
planning a conference, we would appreciate.
And as Srihari mentioned in the chat, the responses are anonymous. So we'd really like your very frank opinion, which will help us shape the way we want to work with the SciPy India community. And we're also uh, we encourage you to volunteer if you have the time and the interest.
If you do feel like it, share it with your peers and friends. Encourage them to submit talks and proposals. I think it's something that uh, not just being a core volunteer, but I feel everyone should have a chance just at public speaking. Could start out virtually online and then ramp your way up to in-person talks as well. And that's if you feel like it, of course. I think word of mouth, especially when it comes from people you know, that's the best way of spreading the word about, and just getting people and uh, just getting the audience to grow every call. So yes, yep.
Do any of you want to say anything about how, if you want to say out loud? I will stop the live stream now. Is that okay?
That works.
Yeah, if like if you're not comfortable speaking on